So this is like some of the variants in the first type, wherein you tune the pMOS current fixing the nMOS current. We can obviously do the opposite also. Let's see a couple of them today. So let us say this, I'll call it B. Here let us say I'm fixing the pMOS current and tuning the nMOS current. So let me quickly draw the single stage differential OTA. So this is the fully differential OTA. Now what we are suggesting is we want to fix the pMOS current. So let us say I bias this pMOS transistor so that it carries some current I0 by 2, right? And that's straightforward. You can basically take a copy of this guy, pass a current I0 by 2 and generate this voltage and connect. Fine. That will fix the pMOS current. And now our goal is to basically make sure that this current is equal to I0, and that will I once again do by basically sensing the common modes here, right? You sense the common mode, have something to compare, and then control the gate. And whatever we saw in the last case, everything can be done here also. But in addition to this, we can do a couple of more things as well. I'll discuss about that alone. See, here the goal is to basically control the current in the nMOS transistor. Now tell me, the current in this transistor depends on what voltage? Strictly speaking, gate to source. Here the source is grounded, right? But that's what we can control the gate. That's what we typically do. But you can also actually control the source voltage, right? And of course, one thing is you can do the same thing. Again, have a op amp, blah blah blah. But now the source voltage here, do you think it will be typically a small voltage or a very large voltage? You want it to be very small, so this might not be a great idea to do. Okay. So if you were to control the source voltage, you can't put an op amp there, but of course you can't go and connect it to ground. So let us say you will put some element here that will incur some drop. Okay. Now let us say the nMOS current here is some IN, and let us say this is the outputs. If I find that, say, the nMOS current is smaller than the pMOS current I0 by 2, what can you say about the common mode voltage? I am pushing in more current here than the current that is getting pulled out, so the common mode increases. So to counter this, what should I do? I mean, to counter this, what should I do to the current IN? I have to increase it, correct? Yeah. If I had to increase the current, what should I do to this voltage? So if I call it, let us say, VDA, I have to decrease PDA, right? So now you see, I find that if basically my common mode increases, I have to reduce this voltage. So essentially I need to have a 3-terminal element, wherein if the voltage in one terminal increases, the other terminal voltage should drop. What is the simplest element that does this? And common source configuration, a transistor. So I can basically replace it by this and feed the common mode. Now again, to generate the common mode, you can do this VOP VOM, but if you do this, once again you will have resistive loading. So if you want to avoid that, you can take a cue from what we did in the last thing. Yeah, so here you again see that we are getting the common mode in terms of voltage, but the final action is happening in terms of current. So you can basically split this one transistor into two transistors like this. I'll feed in VOP here. Here. It's the same thing. So basically, let us say this is this. Fine. So once again, you know that this voltage VDA, do you think it is going to be, you want it to be a large voltage or a small voltage? You want it to be really small. So in which region do you think these transistors are operating in? I mean, this is the drain voltage. You ideally want it to be really small. So in which region? Linear. Okay. So this will be operating in linear region, like mostly like a resistor. Okay. So that is something to note. Let me call, I don't know, how do we call this? Let's say MA. So MA operates in linear region. So this will again set the common mode thing, but the actual voltage to which the common mode is set to will once again depend on the circuit parameters mu and Cox. You have to write the current equation and find out. So you don't have a good control on the common mode in this implementation, but you can actually do a minor variation to this to get a better control, and I'll just qualitatively explain that. So let us say I take an identical transistor MA, okay, and let us say let me say the currents here are IDA, VA, and here it is I0. So what is the current IDA? I0 by 2. So let me write it here. So let us say I somehow make sure that the current in this transistor and this transistor are the same, okay, and I apply the required reference common mode to this transistor, and I somehow copy the same drain voltage here. Okay, so let me say this is, let us say drain voltage is VDB. So what I'm saying is, if I ensure the two drain currents to be equal and the drain voltages to be equal, what do you think will happen to the gate voltage? The negative feedback loop will automatically set it to the same. That is the only possible, like solution to which the loop can lock to, right? So that's a very crude idea. So now we'll have to ensure these two conditions. That is, we have to make sure the same current flows and the drain voltage is also exactly the same. So first thing is the current. So what is the current IDA? I0 by 2. So I have to make sure this current is also I0 by 2. So I have to enforce a current of I0 by 2 here. How do I do? I already have this guy. I can do this. Of course, that will force the current to be I0 by 2. But does it enforce the two drain voltages to be same? No. So let's think. First of all, what is setting this voltage VDA? Yeah, so if you see, if let us say this is some VB0, what is VDA? Yeah, so what is setting that voltage is the nMOS transistor and the current flowing through that, and that is kind of setting it. So this is VB0 minus. So now you tell me a way in which I can make sure the drain voltage here is also equal to this. I need to get a voltage which is VB0 minus VGS at a current I0. So can you suggest me a way in which I can get the same voltage here? If I take an nMOS, say identical nMOS, right? Of course, there is a small catch. The catch is the following. The current flowing here is what? Here it is I0. So what should I change? I should change the width. Okay. So here, if this has a width of say W by L, what should be the width of this transistor? Okay. If I do that, then both of them will have the same gate to source voltage. So as long as this voltage is same for the two gates, these guys will also be same. So which means the loop will, you can work out, the loop will lock to a voltage so that the gate voltage here is equal to this. Okay.
So what's wrong with shorting VD and VD?
VD, okay, you are asking, okay, interesting question. So you do this what? But now see, okay, I'll give it as an exercise now. You think about it, right? This looks pretty trivial, but it will not work. You want to make sure the currents here should be same, right? So one last thing is I have to generate this voltage that can be simply done by putting a diode connection. That's all, right? I mean, that's simple. You can assume that for this is ground, and then if this was ground, you would have done this. I mean, this is clear. What I'm saying is, if this was at ground, to generate the required voltage, you would have just done this connection. Now the only difference is you have a small drop in the source. That's all. So this is also a common technique sometimes used, and I'll call it variant B1. And this is called the replica bias. The notion of replica bias is generally used in multiple places like this. The idea is the following: you want to do something in your main circuit. What you do, instead of directly doing it there, you have a replica of the same thing, do an appropriate operation there, and have a mechanism so that that gets copied here. Okay. And this will find this basic idea is used in multiple, places actually. And one last thing you can do is the following. So here this branch is existing only for biasing purposes. So instead of making this branch carry a current of I0 by 2, which is basically same as the current drawn in this branch, I can scale down the current. So I can basically scale everything, let us say by a factor of 10. Let's say I make it 1/10 the size. Current will also become 1/10. So this size I'll make it 1/10. Basically scale down the current and the widths so that it doesn't consume the same current as your main circuit. So just from the point of view of power consumption. Okay.
So will we get a reference current available on the chip that's not connected to either of the?
Okay, you are asking floating current source like this. That you will not get. So which means you can basically see, this is just an I was just showing it as an example. You can basically do some kind of current mirroring and do it, right? Or one thing you can do is the following: you can put a resistor here. See, the idea behind that is the following, right? If let us say this is a current I0 by 2, if let us say put a current source I0 by 2, this voltage will be set to something, this will be set to something. Let us say it is V1 and V2. Now let us say the resistance is V1 minus V2 by I0 by 2, effective resistance per se. So if instead of this guy, if I put the same resistance, what do you think will happen? It's a substitution theorem. Okay, I mean, what I'm saying is, if we have a scenario wherein I'm reversing substitution theorem. So substitution theorem says if I have V1, V2 and R, I can basically replace it with a current source with that value, nothing changes. Okay. Same thing. So we can either do that or basically have a different current mirror and make sure that our goal is to make sure the current here is I0 by 2. That's all. Okay, cool. So I'll just do one more variant. Satnam's machine, is it? Satnam's machine? It's okay. So we'll just show another it's like disposing a bomb. Okay, good. So now there is one other simple CMFP that is also commonly used, and that is again based on the principle of setting this current to something. So let us say this current is fixed. Okay, the pMOS current is fixed. Now the goal is to tune the nMOS current. So one thing you can do is the following here. So let us say this is fixed to some I0 by 2. I0 by 2. Now let us say I make sure that the current flowing here is some I0 plus 2Ix. That is, it is not equal to I0, but I can make sure that it is greater than I0. Simple. Let us say I bias it to some point so that the current is greater than I0, and let it be I0 plus 2 times Ix. Okay. So now let us say in steady state, if the common mode is correctly set, what can you say about the current in these two transistors? They will be same. So current in the nMOS will also be I0 by 2. So now you see, these two currents, what's happening? Yeah, these two currents are I0 by 2. So the sum is I0, but this is drawing I0 plus 2 times Ix. So to satisfy KCL, what should I do? I should have another current source, 2Ix. Right. So now let us say I find that the current in the nMOS transistor, let us say IN, this IN let us say smaller than the pMOS current I0 by 2. Now what can you say about the common mode? Common mode will increase. So to counter for that, I should reduce the current flowing here. Let me not write it as I0 by 2. It is some IN. So right now this current is smaller than I0 by 2. So the common mode is increasing. Now to counter this, what should I do to the current IN? I have to increase IN. So now remember I have now two current sources. The currents in these two current sources is fixing this current. This current is fixed to, let us say, I0 plus 2 times Ix. So which means to increase the current in the nMOS transistors, what should I do to this current? I should decrease it, right? So you can't have a fixed current source. I should have what kind of current source? Variable current source. But this current source must be varied based on what? Sorry? How did we come to the conclusion that the currents here are not equal? VOCM. So based on what should be controlling the current? So it's not a current source. It's what kind of current source? Voltage controlled current source, right? So I'll just say Ix must be this 2Ix must be controlled by VOCM. So this should be a voltage controlled current source. What is the simplest voltage controlled current source, you know? Huh? Common simplest, a transistor is a voltage controlled current source, right? So essentially, if I somehow feed in VOCM and do this will once again have the feedback mechanism. And to generate the VOCM, instead of using two resistors, what can I do? I can use two transistors, right? I can basically split this guy. So now you see, let us say this current is fixed to some value greater than I0. So now if the common mode is increasing, the currents here will change automatically so that the two currents will be equal. Okay. So in steady state, what will be the currents flowing here? If let us say this is I0 by 2 and this is I0 plus 2Ix. So both currents will be Ix. So what will be setting the output common mode, or what values, to what value is the output common mode getting set to? VDD minus the source to gate of that pMOS. Common mode is the gate voltage for the pMOS, and the loop will lock in such a way to keep the two currents to be equal, and the solution is to have a current Ix to flow in this transistor, so that will generate the required gate voltage. So this is one simple nice thing, a simple CMFB you can use, right? Again, the issue is the common mode is set to some value that is not completely under your control. So this might be useful if, let us say, following this guy you have a second stage. In the OTI, let's say you have a second stage like this. Okay. Now let us say this guy has to carry some current, or I will say, or I'll put it the other way. So let us say now you have a second stage connected, right? Now this common mode here will also determine the current flowing here, right? So nominally, if you want the current in this transistor to be some, I don't know, I3 something, okay? What do you want this voltage to be set to? Let us say, yeah, you want this to be set to what? VDD, VSD of a pMOS at a current I3. So if you can make sure that these two values are same, you can simply do this. So how can I make sure the two source to gate voltages are same? Same thing. So I'll make sure that the two transistors here, I mean all these guys, will have the same. So in these cases, this might come in handy, because
there are two outputs, but you are using only one.
Yeah, I didn't draw. Here also you'll have it. Okay, we'll come to a two-stage OTA later. I mean, basically here also you'll have. I'm not drawing it. We'll come to a two-stage OTA now. Yeah, you're right. This is a fully differential. So just like I have one here, I will have one more copy here. Right. Cool. So to basically summarize, let me see if I have the CMFP written somewhere. Oh. Yeah, so let me use this itself. So this is basically one variant. The second variant is where we tuned the nMOS current by fixing the pMOS current. And here we saw one was the replica bias. And the second is where we had an excess current flowing in the bottom branch, and making sure the extra offset current is kind of flowing in the other pMOS transistors. And even in these two guys, if you see, the output is not connected to a resistor, it is connected to a transistor directly. The output is directly going to a transistor and not a resistor as such. So it will have the same properties as this guy. Okay. Cool. So these are basically, let us say, few of the CMFBs. Of course, once you know the basic idea, you can make up your own circuits.